So hi, welcome to the online audience and the people here in person. My name is Fred Layton. I'm an assistant professor at University of Wisconsin-Whitewater. I teach in a program called Media Arts and Game Development. So my background is in digital media design and development. And I'll let Stephen Gerard, who is in Wisconsin, remotely introduce himself.
So, hi, I'm Stephen Gerard. Yeah, I'm joining you from beautiful Whitewater, Wisconsin. I'm an associate professor of chemistry here at Whitewater. So back to you, Fred.
So yeah, we teamed up to work on this project over the last few years. It stopped and started, but we were looking for a way to perform some specific learning goals, tasks for undergraduate chemistry students that Dr. Gerard has, Stephen has. And so this is what we're talking about here is just a prototype design for using mobile augmented reality custom application to teach specific skills in chemistry, which Stephen will talk about. Why there would be a need for this app that we developed and what we're doing.
Yeah, my function in the project, aside from the say content experience, is for the sake of this presentation, is also to demonstrate that there is a need for new technologies that are designed to help students to be able to learn concepts specifically to chemistry. Because as a chemist myself, I teach in front of students on a daily basis, and I come across very similar issues that students encounter when they think about, say, performing calculations, determining structures, things that are quite difficult in many cases for people to spatially visualize unless you have a lot of practice with them. So in this slide, what I'm showing are the basic ways that we teach students to visualize a very complex issue in chemistry, which are chemical structures. And so if you've ever taken a chemistry class before, you're probably familiar with looking at some of the structures that you see in front of you right now. There are different ways of representing the same exact information. What we usually do is we like to show the chemical composition or the formula. For example, on the left-hand side there, we see the composition of CH sub 4, CH4. This is also known as methane and is the active ingredient in natural gas. So at least here in the US, but I also think in most other societies in the world, when we burn natural gas, say if you turn on your gas stove or say your hot water heater, your furnace for your house, it is most likely is going to be burning that formula. Now, what I require for my students to be able to do, and this would be a requirement in essentially any chemistry class, would be take that structure, take that composition, and then try to draw out what the actual structure would look like. How many bonds are you going to be generating? And then understand from those bonding relationships, what is that structure going to appear like in three-dimensional space? So what we typically do in order to go from the formula into the structure is we have students follow a theory. It's known as Lewis dot structure theory. And this involves then taking the valence electrons, these are the electrons on the outermost shell of each of the atoms. You have to place the atoms in the correct order, and then you have to fill them using bonding and lone pair electrons. If you've ever taken a chemistry class before, you also know that for the majority of the structures that we do, at least in general chemistry, they follow the octet rule. That means that you have to have a grand total of 8 electrons on each atom. Now, students do a pretty good job in the first two parts, right? They take the formula and then they're able to generate a Lewis dot structure because it's a fairly sequential process to be able to do this. But what you'll note is that the structure, if students generate the structure that we see on the screen right in the middle there for CH4, if you look at that, that is a totally valid Lewis dot structure, but it is not a fair representation of the actual chemical structure in three-dimensional space. If you look at the center structure, it looks like a square. It looks like a flat square that you would have, say, with 4 hydrogen atoms that are set up sort of in a diamond formation. But if we actually visualize the structure of methane in three-dimensional space, we have to represent each of those bonding groups, so that would be a carbon-hydrogen relationship, as taking up as much space as they possibly can. And so in actuality, what we generate is a structure that is known as a tetrahedral structure that's all the way to the right. And this is a picture of a space-filling ball and stick model, is what we call it. And that ball and stick model, you'll note, it kind of looks like a tripod. It does not look like a square planar set of atoms. So what we find largely is that when students are trying to go from a two-dimensional representation on a piece of paper or on a screen into a three-dimensional representation that would actually be taking up space, real space, well, that's where the Lincoln learning actually breaks down for many of these students. So next slide, please. So this is a really good example of where this breakdown in learning can occur. This is actually a representation of my very favorite chemical geometry. And on the left-hand side here, we have the correct Lewis dot structure for sulfur tetrafluoride. So that's going to have the composition of SF4. Now, the structure that you see on the left with the series of dots and the series of lines and the S and the 4 Fs, this is a completely valid Lewis dot structure. And many students using the rules of Lewis dot structure theory should be able to generate something that looks like this. But you'll also see on that structure on the left that it appears, once again, like a square array of fluorines around the center sulfur. In reality, if we take the correct VSEPR theory, this is the space-filling three-dimensional model, what we have is the structure of that SF4 molecule on the right. So what you'll see is that on the right, this is the correct space-filling model in 3 dimensions of SF4. It actually generates what we call in chemistry a seesaw conformation. And the reason why it's called a seesaw is because if you've ever played on a seesaw, say in a children's playground, something like that, well, what you'll see is that you have 2 atoms that form the base of the seesaw, kind of like a triangle, and then you have 2 on either side that would be the places where then the kids would be able to sit and go back and forth. And I hope you're able to recognize that the structure on the left, which is completely valid as a Lewis dot structure, in no way mirrors the actual correct chemical structure in 3 dimensions on the right. Okay, so there's a very clear disconnect that can happen with our students, with all chemistry students, when they're trying to then rectify those 2 structures either in 2 dimensions or in 3D. So we have to come up with a better way to visualize these structures in 3D. So next slide, please. Now, in order to help students to memorize the actual space-filling models, we use a theory. It's called VSEPR theory, which VSEPR, it stands for valence shell electron pair repulsion theory. And essentially what we do is we ask the students to make their Lewis dot structures. So the structures you had seen on the left, count up the number of bonding groups. These would be the lines, essentially. And then the number of lone pairs on the central atom, those would be the number of dots. And then using those 2 pieces of information, they then can understand what the molecular geometry would be. So that's highlighted kind of in the middle of the slide here. And then likewise be able then to relate that to the bond angles. And so what I found is that this is material that in many cases the students will just memorize this, but they don't really have a super solid understanding of what it means for a structure to be tetrahedral or for it to be trigonal pyramidal, for example. And so this is also what we're trying to address with this technology. So next slide, please. So we can think a little bit about what current tools exist for students to be able to understand these structures in 3 dimensions. And if you've taken chemistry in the past, you're probably familiar with ball and stick models. These are going to be physical models that in many cases you have to purchase out of pocket. In many cases, they can cost upwards of $20. I think nice ones are always upward of $50. So if you're a science major, you have to pay out of pocket for it. Likewise, these are going to be physical model kits that require for you to assemble them. So you have atoms that have holes, you have sticks that you then have to pop into the holes. And I actually have a vivid memory of myself being an undergraduate chemistry in a large lecture hall with a series of years and having my model kit out with all the little balls and all the little sticks and fumbling it and all of the balls scattering all over the lecture hall, right? Going down all of the concrete tiers. And it was really embarrassing, right? So what you'll note here is that for ball and stick models, there's always going to be an element of user error. It requires the students to actually have to build them. That can be frustrating. It takes time, etc. But ball and stick models do a really good job of visualizing in real space, the space that the students have. So in order to address this, there have been some online models that have come into play in the last few years. Now, these are really helpful because they're highly accessible. Students can access them on their smartphones or computers. They're very simple to assemble because you don't have to physically assemble anything. The fundamental issue that exists with any of the online modeling kits that exist is that they actually cannot be used or visualized in real 3D space, the space that the student actually resides in. They always are going to have to instead look at these online models on still a 2-dimensional representation of a screen, right? So what we want to do, so next slide, please, is to try to take the best parts of both of those halves. That is going to be, how is it that we can visualize the structure in real 3D space that we would get from a ball and stick model, the actual, say, physical model, but then how is it that we can also get the improvement in accessibility, improvement in cost, and the simplicity that would come with a virtual model kit. So in order to rectify those two halves, those two benefits that we get from those two different types of models, what we are trying to do now is bring them together in an augmented reality model kit that is hopefully going to address many of the issues that students have with learning these structures in 3D. And so with that, I'm going to go ahead and just pass over the remaining portion of our presentation to Fred so that he can describe to you guys the technology in a little bit more detail.
Okay, so great. So I'm okay on the microphone? Yeah. Okay. Okay.
I hear you great.
Okay. All right, great. So thanks, Stephen. So, you know, okay, great. Thank you. Yeah. So, you know, as Stephen was saying, the really the learning goals for this app that we've developed is fairly simple, really, in that it's a very targeted, you know, set of information and learning goals. The students need to, in the interface, you'll see they need to choose the number of bonding groups that they're working with, and then they choose a number of lone pairs. So from that chart that you saw before, there's 2 pieces of information that they need to input into the interface or choose from the interface, and then that results in information that they get back. So when they make that choice of the lone pairs and of the bonding groups, they then get back information that reflects the molecular geometry, the bond angles, and then the actual 3D model is in augmented reality. So all of that other information in the chart that was connected to, you know, that choice, those 2 choices, what is the result? So here's a brief video, just a couple minutes, showing it in action. So here you see me using a visual marker, an image. That's our school mascot, Willie the Warhawk. Whitewater is the Warhawks is their sports teams, our mascot. So anyway, so we use him as a visual marker, but it could have been any image. We're using the technology here is Vuforia is being used to handle the augmented reality. And so you can use visual markers in Vuforia, you can use objects as markers, you can use different things. So you're not stuck with the old blocky, super pixelated AR markers that we used to have. So that's just a choice that's made. That could be any image. And so the image, the placement of it, as I'm showing the rotation of it here with my hand moving it, both the size of the marker image and its orientation in space drive, however you've decided to make the relationship between the model and the marker, it's going to stay in that relationship. So if I lifted up the marker in space, then the model would move with it, right? So that's just kind of showing there. And we just have kind of a neutral background there. But you see here in the interface that, like I say, in the top, you make a choice of your bonding group or lone pair. Then that's reflected back to you here, what you chose. And then the angle and the geometry information is given back to you. So, and then the actual model is appearing there. And so this is on a Google Pixel smartphone. And so then you see, like, here's the methane molecule that we were looking at earlier in the talk. So this gives you a good sense of, it's easy for the user to just kind of flip through and try different combinations and see what the results are as they're learning. And so, we're interested in, I think, does this help students? Is it something that, just by being a novelty or just being something kind of fun and interesting or different, does that help them in some way? We may try to measure that with students later this year in Stephen's classes. But here you just see kind of a general demonstration of, of this. And so, people always say, oh, Pokemon Go, or something like that, because that's a go-to AR reference. Everyone knows Pokemon Go. So this, so this is Pokemon Go, but it's with molecules, right? So on the development side, just to mention, I used Blender, which is a free 3D modeling tool, very good modeling tool, to make the models, which were relatively simple to make. Unity is the interactive authoring software that was used to make the app. But Vuforia works well with Unity. Vuforia is the augmented reality technology. So Unity has some different ways that you can deal with augmented reality that have gone the last few years, but Vuforia is something that I've worked with and had a lot of success working with within Unity. So really, that's about it. Any questions or anything, we'd be glad to ask. You can also reach us at email here at University of Whitewater, uww.edu. But so I'll give it back to the chair if there's any questions that we can answer.
Thank you very much for your interesting talk. Are there any questions here in the room?
Yeah, what's the lead time to how much time do you need to put something out there like that?
I think that I guess I could say, we started working on it in 2019 as an idea, and then put it on the shelf. Didn't really do anything with it for a while, and then kind of had a renewed interest in it because I teach a class on mobile augmented reality, not every semester, but every year or two I teach a special class. And so whenever the technologies change and start to get new techniques and things like that, I then kind of rethink, we could maybe revisit this project we were working on because now there's some developments that would make it easier to do some things. And so we just kind of revisited it, and I think really it's just been over the past 6 months or so, just kind of pushing it along, kind of furthering the prototype. But if you're able to learn the Unity and how to work with Vuforia, that's the kind of the technological hurdle. But once you get past that, it wasn't too complex. It's not a very complex program, really. It just has the one single interface right now. We haven't designed anything else into it. But for right now, that's the way it looks. So it's really just a matter of getting the augmented reality part working well, and then also trying to figure out a way to design the interface to have it to be usable, so that the information you're getting back, so that you're understanding how things are working. But like I said, it's a very, very specific, set of content we're trying to teach. So that helps to make it kind of easier in some ways, because you can kind of say, well, this is, 2 inputs of information, and then we're getting this, 3 outputs of information, and so it's relatively easy to program once you get to that point. But yeah, I don't know if that answers. Yeah.
Thank you. Any more questions here? I have a question. Did you involve the students during the development process and presented them the first version of your model?
We are now. Yeah. Dr. Gerard is doing that now.
Okay.
Yeah. We just got it to this state recently that you just saw here in the demo, and I'd be happy to show it to anyone here. I have it on my phone if you want to see it actually in action. I can show it to you here in the conference. But he has started to get input from students. Yeah.
Cool. Yeah. So I'll jump in there. I'll tell you that I have shown it to smaller groups of students. I haven't implemented it yet in my class, because I normally teach a class of at least 100 students, and we want to make sure that the technology is at a point where we're able to have it stable for 100 students working in the same space. So I've implemented it now just for a handful of students on a one-to-one basis, and so far everybody thinks it's really cool, right? So I think that there is a benefit to having a wow factor to any new technology that's used in learning, and that's what we've been able to accomplish. But the long-term goals of this project is also then to look at specific learning outcomes of the students. We use the same types of assessments every semester, and I can then pick out from those assessments specific questions that are going to be focused on the theories that are addressed by this technology. And our hope is that we should be able to demonstrate before we use the technology versus after that we use the technology, that there's an increase in student learning via their test scores.
Very good. Then thank you very much to both of you for your very interesting presentation. And I hope you can show it to us later on after the session.
Let me
it
know.
would be nice to see.
I got it right with me.
Thank you.
And thank you very much.